thank you very much. Thank you very much for the invitation and the great opportunity to talk about our recent research results in this wonderful place. This is where we are from. Okinawa is a South Island in Japan, and we don't have these beautiful mountains, but instead we have a beautiful ocean in front of us. And this work is actually collaborative work, so I'm talking about this, but there are two people, researchers up there, Kitabe Sakurai and Aoi Hayashi contributed hugely to this work. So looking at the work on computer development in the history, maybe 7 or 8 years ago, we started to see the quantum machines online available, starting with probably the first one is the INQA 5-qubit machine. But since then, it developed quite rapidly, and in 2019, this famous global paper is out, which has 54 qubits in there. And 2 years later in China, we have seen 62, and now last year we have seen this, over 400 qubits in this kind of machines. And of course, at the moment, there are lots of efforts towards quantum computers aiming to create over qubits. However, there are, of course, still huge gap, technological gap between 400 qubit machine and over 1 million machines. So we have to see the more technology development to fill this gap. On the other hand, of course, we have asked ourselves what we can do with this kind of 50 qubits. And the reason is, of course, in the long history, maybe not that long, because the quantum computer history is not that long, but from the beginning of the history of quantum computer development, 50 was kind of sort of landmark to achieve, because if you have 50 qubits, it starts to difficult to calculate what's going on in that kind of quantum physical system. So to think about it, what it would give us if we have 50 qubits. Then, if you think about it as a network, of course, it's not a real network; it's a virtual network on qubits. But if we think about that kind of dynamics as a network, then it is almost as large as human brain in terms of node size. So we should be able to do something, but it's not very successful so far. And another way is that at the same time, if you look at quantum annealer, we have 2,000, 5,000 qubits, but of course these are different from these machines. And what kind of complexity can we get and can use for something useful? That's the kind of question behind all this research. Going back to the beginning, we start with very simple. So here is just 1D array, and quantum annealer is not coming out very soon. Have to wait until there's quite later in the talk. It's a sort of more quantum annealing type of thing. So we're starting with a quite different system, but just to give me a bit more time to get to that point. So we have this kind of 1D array, and the qubit is, so this is superconducting qubits. So here we have still a bosonic representation of the Hamiltonian, and we have site energy. It's non-linearity in there, and we have coupling, which is nearest neighbor coupling between them. And so we have that this is a realization in China, this 12 qubits in there. So it's one-dimensional because it's only have a nearest neighbor coupling, so we consider it 1D. And now we like to modulate this on-site energy or Hg in here, which is coupling, or could be both, but to make it simple, so just modulate this H, which is on-site energy, and what we can see. Then if we do this, then we can see that if we don't have the modulation, It's a localized state. But because of the modulation, then you can start to see that's ergodic nature in the state. So that's dependent on how hard we actually modulate this. And what happens if we have these kind of connections? Half is ergodic state and half is localized state, but we just have only this edge qubit, the end qubit, to be coupled, and what happens? So that's the first question. And can we see it in a network representation? So here, this part, this is a Hamiltonian in the matrix representation. So it's just to write it in a numeric way. And here is more or less localized state, so there is no hopping terms. That means it's localized. But here is more ergodic term because it's kind of doing much more chaotic dynamics. And if we have some, so this one is ergodic is not that strong, so it doesn't really count to the localized part. But if we have more ergodic nature in here, that started to leak out, and that actually dictates the entire system. So it's not really, we are not changing that's the modulation in this region, but still this ergodic nature is so strong that it's kind of leaked out. And because we now wrote the Hamiltonian in the matrix form, then we can think about network corresponds to this. And it's interesting to see that this kind of natural sort of leaking that property out, and we can see more scale-free network. And if we have completely ergodic, then we have more sort of random graph in here. So to see this, just going back to see what we have done, then we have this sort of the other way around, but this is the ergodic region, and this is the localized region, so this is interaction in between them. But then we have three terms. Then now we are modulating this in that Floquet way, so it's a periodic way. And so we can see the Floquet operator in capital T. So you start from T, and at T plus capital T, your Hamiltonian go back to the original Hamiltonian, which is HT. So in this case, so HT is the same as HT plus T. So then this unitary operator, we can think about corresponding Hamiltonian, we call it effective Hamiltonian, then we can map that into numerical representation in the matrix, then we use the population rule, then we create the graph. So this is the one way to understand the dynamics instead of sort of looking at that, so sort of understanding that in terms of network picture. Then now move to a little bit more interesting phase, which is a time crystal. Here's a discretized time crystals realized 2019 using ion trap system. And this one has three sort of, again, periodic control, and we can again think about from operator, therefore we can calculate effective Hamiltonian in here. So in this way, we can sort of turn this into network picture and see if we start to melt the time crystal. So changing this epsilon here, we can start melt. So if epsilon is 0, then the time crystal is perfect. That means one state goes to another state comes back. So that's 2T DTC we are looking at here. So it looks like in the network picture, it's like a diamond record. So it's not a pair. So it's going back and forth. But what happens if we change the epsilon? And then we start to see the time crystal melt. So just let's see what happens. Oops, it didn't work. So there are some kind of preferential attachment and that is dependent on domain wall. And then we can see that some certain states are more likely to connect to others. So therefore, on the way to completely random graph, we will see some different structure. And now this movement is just artificial, so don't think about it as a movement. This is just a computational artificial effect. But if you cut some picture out at a certain epsilon, then you can see now clearly the scale-free nature of the dynamics. And if you have almost completely melted, then we have for random network. So there are some sort of transition from scale-free network to random network. So the next question is, okay, we can see that sort of non-trivial, like scale-free network, non-trivial dynamics, but is it possible to do something practical? Okay. So we're coming back to this, and we see this one is again the same model, and just to see some kind of feature. It's a bit slow, but then if we don't wait enough, even though dynamics is complex, but the network hasn't grown it yet. So if we want to use it, of course we have to wait a certain time, then do something. Otherwise, we cannot get that effect of the complex network. But that is quite understandable, because the quantum computation should require some time for computation, so that is not strange. But then we can insert that structure into some kind of computation model. And this is, roughly speaking, I'll explain what it's doing better, but it's kind of classical input. It could be quantum input, but it's at the moment just to say classical input, and use this virtual network on the Hilbert space. And then we have some kind of classical, this is a hybrid system, so it's a classical neural network, and we have output. So that is roughly speaking. And doing so, what the question we are looking is, okay, this is a classical neural network, and we think this is a computational resource, that why if the problem is difficult, we have to have more and more hidden layers over the number of nodes. So if we think that this can be the same thing, that means we really believe network on the Hilbert space, virtual network on the Hilbert space is actually useful, which is, you can think about a computational resource. So that's true or not. So it really works as he just said. Now, of course, this is not the first thing people thought of it, and the most maybe famous one is this type of quantum circuit learning, and particularly probably the most famous is the variation of quantum algorithm. People use a lot of this method. And here you have purely quantum part, which is input layer, and that is usually called feature space. But it is known we have to have a good feature space, and that requires quite a long, complicated quantum circuit. That means to implement it, you need a certain time to implement it. So it's a little bit difficult when the quantum computer is noisy. And here is a hybrid system, which is here, this part is quantum, but the calculation is estimate constant cost function is not quantum. This is a classical part. Then you update the operator and you run it again. It's until we get the optimal point. However, there is some programs reported. Basically, for the program, it's difficult to actually optimize this because almost everywhere becomes getting flatter. That means it's hard to optimize using this kind of cost function. So that is what we have seen. Another method is maybe Carnot method we have seen, and that's actually used to do some classification programs. So this program is done, is sort of the original program is like this, and you can see the red dot and blue dots in the different regions. So the question is if you can classify the red is red and blue is blue. And this is typical, very simple test program for nonlinear program, because if you have one here, and if you put line here, then you cannot really sort of classify them. But once you go a higher dimension, then you can just classify it, just put in one layer. So it's become a program in higher dimensions. The problem is in classical, this kind of method is relatively easy to implement, but in quantum, because you have to have the same length of the U-J to invert it, so that is very difficult in running the NISQ processors, for example. So you can see that the result is quite noisy in this sense. Okay, so these are sort of typical examples we have seen using NISQ processors. And another example is another direction of using this kind of small scale quantum systems for computation. It might be quantum result computation. So these things should work if, well, in some extent should work if we have very, very accurate gates, which sort of doesn't contaminate, particularly Carnot method. If it doesn't contaminate, that's the circuit, and it should work. But the problem is we have only noisy qubits so far, and here is a bit more difficult because of this optimization program. But another thing is sort of forget about all these sort of precise control of the quantum system and pick some quantum system and use it as a reservoir and do some computation, sort of referring reservoir computation. So what is a reservoir computation? So instead of having this kind of artificially created hidden layers, we insert some kind of physical system which is complex enough and use it as a computation resource. And here is a weighted network, and we can optimize this output, output network, to make this sort of complex useful for computation. So that's what it's doing. And to evaluate it, they usually people sort of think about to run that system and say how well this predicts the real answer. But that is not very useful because once you sort of, if you have to run sort of program to evaluate it, it doesn't much help to design this reservoir. So sort of, it is nice to see it, but again, it is not very useful when you're thinking about designing quantum reservoir. And people thought of it, and there are several properties that the reservoir has to have, and one is nonlinearity, and another one is high dimensionality, and that also temporal memory. So temporal memory is coming from that sort of classical computing, classical reservoir computing, typically used for temporal data analysis. So that's why we have this. And we can see that it's also inherited to usual quantum reservoir computation. So this is an example of quantum reservoir computation. And in this work, some kind of ensemble measurement introduced to induce nonlinearity in the system. Otherwise, everything is linear in quantum dynamics, so you have to have some kind of nonlinearity. So this measurement is doing that much. And then run this sort of reservoir computation for temporal data. And this is kind of direct translation or interpretation of the reservoir computation in the quantum world. So you can think about the memory capacity because they are, because of this non-linearity measurement, the system will lose information. You put it in some time ago. So then we can think about exactly the same way the memory capacity in the quantum reservoir. However, these sort of properties in this quantum reservoir computation, actually there is no necessary to, there is no obligation to run temporal data. That means, strictly speaking, if we're only thinking about using quantum reservoir as a reservoir computation, then it will have no sort of high dimensionality. But it's not necessarily we need to feed temporal data and think about temporal memory. So if we have, for example, image data or other type of programs, then we can kind of get rid of this condition. And then, usually quantum reservoir computation is evaluated by a memory capacity, but then we don't need to have that constraint. And we can use that quantum reservoir for some other programs as well. So that is one thing. But still, you know, it's okay to get a hint from classical computation model. So start from 2 layers, so it should be able to run. To solve, if we have big enough hidden layer, then we should be able to solve problems. And then we're thinking about this to be extreme machine learning model. So that's quite similar, but we now have this part is a random network. And then we can optimize this part of the network, then we can sort of solve a lot of different problems using extreme learning machine. Okay, so this is something sort of is close to variational quantum computation, but it's not exactly the same. And another way of looking at this reservoir computation, it's somehow similar because we both have a fixed neural network. This part is fixed and this part is fixed. Of course, we don't know what kind of neural network we have in the reservoir, but in some sense, then we optimize this part. So there are some similarities. So in some sense, that's what we looked at as quantum extreme reservoir computation model. We have is kind of combined in a sense, because then we have here now is classical computation process. It looks like reservoir was became quantum, but also it could be considered as a sort of random network was replaced by the quantum reservoir. And it looks similar, but it's not sort of kind of the both nature combined to have this new type of model. And we have to have one more sort of layer in here because we cannot really have quantum state into the classical network naturally. So we have to have some kind of layer in there. So there are some differences. So this is what we're calling quantum extreme reservoir computation. And using this new model, we're going to see how it can be implemented and what kind of property we can get and what kind of physical property contributes to the performance of this model. So we wanted to answer these things. Of course, we cannot really answer everything at once, but some part of it is getting quite clear to us, and one way of doing it is to evaluate it. Of course, we can evaluate the accuracy, but then what kind of property we have, then we start to think about network property. Then I don't know if we looked at Hayashi's poster at the end of the corridor, so using network science to characterize quantum reservoir, for example. And this one is, of course, it's a quantum reservoir computation because we do not touch this part at all. So it is a quantum reservoir computation in that sense, but we are not dealing with temporal data. And it is similar to ELN because we have two layers in a sense. So, but it's not without two layers. So it's a little bit extension of. So it is, that's why we say it is extreme reservoir computation. So this is a whole model when we run some kind of programs. We have here is we first use Inst image data, and that's have a bit of classical preprocessor which we use PCA. And then we can put that into the quantum input state, so initialization of that quantum reservoir, and that is done by only single qubit rotation. And in certain time, this sort of dynamics develop to a complicated state, and at the M layer, the measurement layer, we measure all qubits on the computational basis, and then we can get one. So, implementation, of course, we can do implement this on the NISQ processors, but also we can use some other more simple, more sort of robust or more high accuracy system because we don't need that amount of control which is required in these processors. Then now, here we know now we need to have some kind of dynamics, quantum dynamics, then we have to figure out how we put that classical data into the input state, then that will be program dependent, even though this part is not program dependent. So that's what I was saying now, and we want to make this part as simple as possible. So to see this before going into the image image recognition, we use that example we used before and see how that quantum computer is thinking in a way. So this is a time, so we see that if time goes on, computer can actually put a boundary between red and blue. So about 24 or 5 for this NT is 24.5. It's kind of starting to converge to the boundary, and at 30 is almost perfectly classified. So now we can think about classical data, so image data, and this one is MNIST data, but it has 28 pixels, and previous model using tensor network was required quite a lot of qubits, 28 times 28 basically, but that is too much for us, so we use PCM. And we just pick that first, if we have n qubit, we only picked 2n most important parameters, and encode it into theta and phi on the graphosphere. So that's why we need only single qubit rotation. And here is performance. And you can see interestingly about such a regime for the rotational error epsilon to create scale-free network, we achieve the best accuracy here. So at about 97% we can achieve theoretically with 11 qubits here for testing. And here is the training accuracy. Training accuracy can reach almost 1. So the question now is how we can simplify this model. So this model we use is time crystal model we use to 2D DTC model, and 2D DTC effectively Hamiltonian. Actually, if you want to replace the real Hamiltonian, then that means you need multi-parallel coupling states, coupling terms, and that is very difficult. So that's why we have to do in this Frobke way. But is it really necessary? Do we really need many-body Hamiltonian to realize or to make this system working? So we just reduce it to two-body Hamiltonian and see if it works. And if we do that, then we can see this kind of just a two coupling chunk and one transversal field along the x-axis. That's almost the same as quantum annealer. So we can reduce that system dramatically to this kind of system which is already realized and see if it works. And actually it works almost in the same way in here, but it's a little bit more stable in terms of this G term. But anyway, so it's looking at this thing is over 97% with the same accurate number. So that means this model works as better to understand this model. And thinking about this trend, now so you have this peak and coming down. And why this is happening, it seems that this magnetic field is giving the tendency to the dynamics, and that's kind of preventing the system, the model to perform well. So we changed that to test it to have, also the data has a tendency as well. In the classical neural network or classical machine learning, the tendency mismatch between the data and dynamics, it doesn't give us good. So if we kind of cancel that out by a randomization of each qubit by SU2 rotation, then see, so you can sort of reduce that. This sort of delete that effect completely. So that's we can delete the sort of tendency in the data is cancelled it out, then that magnetic field doesn't do anything bad to the system. So actually, we can have this no problem, but then what about if we have XX? With XX, then of course this is just only a transformation, but then we can sort of have a UN symmetry where we can just only have that term without this magnetic field term. And again, we can see it works quite well as well. But the interesting thing is then we think about what is nearest neighbor happens or all to connect, because this particular alpha, it gives us some kind of system symmetry, and it doesn't, you can see if the system acquires additional symmetry and sometimes prevent the system to work well. Okay, so we reduce now is to very simple system to do this kind of classification problem. But actually, it is not only Okinawa classification problem. So it will be specialized machine, but its usage of that is not necessarily specialized. So that might be quite useful to be realized. So here's summary. So there are a few nice points we can sort of summarize. One is fast optimization, because we have only one layer classically to optimize, so it's very easy to do. No programming is necessary in the quantum part, and no update or anything for the parameters, so that's also very easy. And exponential advantage in the terms of the quantum resource, because we now have clearly using Hilbert spaces, Nemoto Hilbert space, so we have to the end after. Also, QERC can perform much simpler quantum systems. That's, I think, always Akitada's paper in the corridor I've seen it, is showing the optical implementation of so qubits, optics, ion trap. So many sort of quantum systems can be calculated. And we can run different tasks without programming. That's another thing. So I think this kind of direction can be another direction we can pursue to think about sort of applications of quantum computers. Finally, We have a competition, so if you are interested, please contact me at Skyline.net. Thank you very much.
All right, let's take this. Are there questions? I actually had two questions. One, I wasn't clear when you were talking about the, trying this out on the quantum systems. Are these simulations, or were you using quantum hardware? In the data that we were seeing with the performance graphs.
Here.
For example, yeah.
So we train the classical part, and we are testing different level of matrix DTC. So here it's 0. That means it's perfectly DTC, so it shouldn't have any complex dynamics, so it shouldn't perform well. And we know around here there is a transition from scale-free network to random network. And we assume it should perform around there. So this was first target area of epsilon.
And this is a numerical simulation?
Yes, this is numerical simulation, calculating the state. So if you do that in experiments, you have to do something.
Thank you. My other question is, I don't know very much about the area, and I was wondering if, in gate model computation, there are theorems that certain algorithms should perform well in ideal, under ideal assumptions. And we don't have a lot of theorems in quantum annealing, and I was wondering about, you're saying these ought to work, and I'm wondering if there are any theorems along those lines, or is it similar to quantum annealing? It just seems like a good idea.
Yeah, that would be a good idea, but the difficulty if this was combined with classical one-layer optimization, so we can characterize quantum part. But then if we fit into the classical part, then that's doing something different as well. So that's kind of difficult for us to prove something in general.
Sounds like the same situation in quantum annealing. Are there any questions?
While we're on this slide where you're actually working with the Inst data, how sensitive did you find it? So to get the results, please, yeah, how sensitive is it to the parameters?
So here it's quite flat, so it's not sensitive to the parameter very much. And also, if you move to a much simpler model, like just like a annealing type of this kind of model, then you change alpha a little bit, it doesn't matter. So it's not really, it's only shows some different nature when system has some kind of symmetry. So if it's really strictly all-to-all coupling, it's the same equal coupling strength, then system has some kind of symmetry, then that prevents the model to work well. But usually that is very difficult, right? So it has to be really equal. And if you have a slightly different parameter for the strength, then you will break the symmetry, then it will be more like that. So I think to perform well, if your model is right, then I think it's quite stable in terms of parameter value.
Okay. And these are pure quantum systems that you're simulating? Or
Yes. This is what the data we show here is pure picture, but actually we run with some noise as well in the simulator. But as far as we can see, it's still working in quite the same way.
Okay. Thank you.